All right, in this video, I'm going to talk about the binomial distribution and the Poisson distribution. So, for something to have a binomial distribution, it must meet the following rules, and these rules are on page 200 in our textbook. So, the process has to have a fixed number of trials. That means you must know how many times that the observational study or experiment is going to happen. The trials must be independent. We learned independence in chapter 4, right? One outcome has no effect on the other outcome. The trials must have only two outcomes, a success or failure. And success doesn't always have to be a good thing. It just means all success means in a binomial distribution is did what you were happened for did what you were looking for happen, right? And if it did, that's a success. If it didn't, then that's a failure. So it either happens or it doesn't. And then the probability of success remains the same in all trials. So once you know the probability of success, it has to remain consistent. And if your trials are independent, then your probability of success should remain consistent. Right, and we'll do so a couple examples of binomial distributions. Flipping a coin, right? If you flip a coin, it's heads or tails. And if you're counting heads, heads would be success. Tails would be your failure because you didn't get a head. The probability of getting heads is always 50% when you flip a coin. Then you just decide how many times you're going to flip it. And once you decide how many times you flip it, then that becomes a binomial distribution. And then passing a test, right? You either pass or you don't. That one might even not be binomial because some test reads are passed and others, so not every test has the same probability of passing. But so that's where it gets tricky, stuff like that. Rolling a dice, which is what we're going to talk about in a minute, can be a binomial depending on how you set up your events. So let's talk about what a binomial distribution function looks like, right? So it's usually represented by b of x. And we have, I'm going to break it down into three different parts here. So first thing we have is this NCX. Remember from chapter 4, NCX is combinations, right? Remember combinations was you knew how many times you were doing something and you were picking so many things without replacement. And then you knew how many you were picking. So that is that formula from chapter 4, combinations. So I didn't write the whole formula, I just wrote out the symbols. And we talked how to use a calculator to calculate that piece. So that's combinations. Then the next piece is p to the x, right? So p is the probability of success. So once you know rule 4, you know p. X is your event, right? We've been talking about that since chapter 4, what you're looking for. So that is your event. N is your trials. So once you know how many times you're doing something, that becomes your trial. So rule 1 and 4 basically give you the values you need for the formula. X is what you're looking for. And then our last thing is 1 minus p, which is our failure. Which we usually call Q. So either Q, which equals 1 minus P. So that is our failure. And it's the complement of P. So once you know P, I can find Q by subtracting it from 1. They're complements of each other because there's only two outcomes, success or failure. And you can't have success and failure at the same time, right? So therefore they are complements. And then it's just putting this into your calculator. And we're going to do an example here in a minute. To find the expected value, right, that is the formula from 5.1, where we had to take x times p of x and then multiply them all up inside our probability distribution function, right? However, if it is binomial and binomial only, expected value is n times p. And if we want to find our variance, is n times p times 1 minus p, or n times p times q. And remember, if I want to find standard deviation, if I want to find my lovely sigma, well, that is the square root of the variance, so that is the square root of n, p, and q. Pull a tail on it, so you don't think that's a 9. All right, or the square root of the variance. So that is kind of the binomial, how you, the formula works, and some of the unique things about it. So what we're going to look at now here is, if we roll a dice 10 times and record the number of trials, that we roll a 5 or 6. And if we were in the classroom, we would do this. I would actually have you all roll a dice 10 times and record your results so we can talk about these things. But for now, we're just going to assume this is, we're just going to do the probability distribution of it. So is this binomial? Well, we're rolling a dice 10 times. So my trials is 10, and that is our n. All right, and our success, I'm going to text this so it's a little bit easier to read. Our success is we roll a 5 or a 6. Right? So if I roll a dice, I get a 5, that's a success. I roll a dice, I get a 6, that's a success. If I roll a dice and I get a 3, that is a failure, so it's not a success. So I either get a 5 or a 6 or I don't, and I'm going to roll a dice 10 times. So what I want to know is calculate the probability you roll exactly 4, which then means x equals 4. The word exactly is equals. So now I have everything I need to solve this. So I do 10 is my n, combinations, remember it's under your probability key, my x is 4, I'm going to times that by my probability of success, right? So we don't know what p is yet. So p, right? How many sides are there on a die? There is 6, so there is my total. And there's 1 5 and there's 1 6. So 2 of the sides have 5 and 6. So the probability of success is 1/3. Right? And we've talked about this before in chapter 4. Rolling a dice is already independent. So therefore we have proven this is binomial. So my dice roll, my probability p is 1/3. And then x is an exponent. So I'm going to raise 1/3 to the 4th power, right? And then I like to put in parentheses here, just so I remember that I must do the subtraction first. 1 minus 1/3. And you could do it in your head if you want, right? 1 minus 1/3 is 2/3, but that's up to you. And then I'm going to raise that to my n, which is 10, minus my x, which is 4. Now, if you're going to put this into a calculator, let me change my color, I would recommend that you put parentheses around your exponent, right? And you must also put a times in here in your calculator. So I know you can't see what I'm going to do, so I'm going to just talk about it here. And we're going to solve this thing. So I grab my calculator. I'm using my Casio FX300 ES Plus. So first thing I do is I put in a 10. Then I hit shift divide to bring up the C. If you're using your Texas, it's under your probability function. Same with our Texas calculator. So go to your combinations key like we did in chapter 4. Find combinations. Then I put in a 4. Then I hit the multiplication sign. Then I put in my fraction. I'm actually going to put in parentheses just to make sure that it stays where it's supposed to. So parentheses, 1 divided by 3, close parentheses. Then I'm going to raise it to the fourth power. So it's the little caret key or the little X to the box on the Casio times, use your arrow key so make sure you're not still in the exponent, times parentheses 1 minus 1 divided by 3, close parentheses, again, raised to the power, parentheses, 10 minus 4. So I type my whole thing in all at once. And the reason I do that is if I type this in correctly in my calculator, I can use the arrows on my calculator and scroll through and see that it is typed on my calculator exactly how it is typed here on the page. And then I hit enter. And I get 0.2276, which is approximately, and there's more numbers after that, but that's just going all 4 digits, 22.8%. There is a 22.8% chance that if I roll the dice 10 times and count how many 5 or 6s I have, I will get a 5 or 6, 22 or about 23% of the time. So just under 1 out of every 4 rolls. All right, so let's do another example. Oop, I forgot my drawings. That's the problem with doing drawings. It doesn't like to stay where I put it. Ah. And let's see here. Oh well. Calculate the probability that you roll at least 1, 5, or 6 in 10 rolls, right? So now the key word here is at least. And hopefully now after chapter 4, you remember at least has a important thing. When we see the words at least, we should think of complement. Because at least 1 means I can get 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10 5 or 6s. But I don't want to calculate that many times. So if I find the probability of 1 minus the probability that I get none or no 5 or 6s, right? Then that means 1 minus p or x equals 0. So I do exactly what I did up here. I just now put everything to have all my 4s become zeros. So 10 C 0 times 1/3 to the 0 power times 1 minus 1/3 raised to the 10 minus 0 power. Now this is not too bad to calculate. Anything 10 choose 0 is just 1. Remember from algebra, anything to the 0 power is also 1. So 1 times 1 is 1. So all I have to do is figure this out. Well, 1 minus 1/3 is 2/3. And then 10 minus 0 is 10. So 2/3 to the 10th power. So 2/3 to the 10th exponent is 0.0173, or approximately 1.7% chance of getting none, right? However, remember, that's not what we're finding. We want to find at least, so we have to go back here to this formula and do the complement. So this is 1 minus 1.7%. So 1 minus my answer, 1 minus 0.017. 98 0.3%. 98% chance that I will get at least 1, 5, or 6 when I roll it 10 times. All right, the last question, which is going to cause everything to move because I haven't figured out how to keep my notes on my OneNote. But it basically says, how many times do you expect to roll a 5 or 6? Well, things where they go. Well, remember, when you roll a 5 or 6, your expected value is n times p. So I just take my n. I should have been doing just using their draw, right? N times p is my expected value. So my n is 10. My p is 1/3. So my answer is 10/3, or approximately 3.3 repeating. So a little more than that, we expect a little more than every 3 rolls, we should get a 5 or a 6. No, sorry. In 10 rolls, I expect to get a 5 or 6 a little more than 3 times. So somewhere between 3 and 4 times, I should get a 5 or 6 in 10 rolls. So that is the answer to part 3. So that is how we do binomial. Now, just like before, right, I'm going to clear my drawings. Next time I'll remember to use my pen on my app here, so it's a little easier. And then I'm going to share my Excel now, as soon as I get rid of my annotate here. Right, so this is the Chapter 5 Excel that's on the course page. And I'm over here at binomial. So what do we have in this Excel already built is, I got my little table up here we did in class of how to sum dice rolls. So 6-sided die, 6-sided die, and inside the box is all the sums. So this function down here below it is that I sum to a 7. And it's binomial because I either roll a 7 or I don't, right? A sum of 7. And I'm doing it 10 times. I don't know why my Excel's moving on me here. We're doing it 10 trials. So I've listed out 0 through 10 for my x's, and then I use the Excel function binomial dist to calculate this thing. So I'm going to just redo the 5 or 6 one because that's the one we were talking about. So I will delete all of this. Right? So in Excel, you can type in the function equals binomial, spell correctly, binomial dist. Right? So the number of success is our x, right? So that my first one is 0. My trials is 10, so I have that written up here. So I'm just going to call that there, or you can just type in 10. My probability of success is 1/3, which is right there. And I am doing a probability density function or distribution function. Here, Excel calls it a mass function, which is technically what it's really called. So I want to put in false. All right, I'm going to lock these cells by putting in $signs or hitting function F4 because oh no, I do want that one to change, sorry, undo. That's my X, so I don't want that to happen. So get my $signs there. I want my trials to remain the same, so I'm going to lock that one. Because 10 trials, and my probability doesn't change because that's the rules of binomial. Sorry, I hit delete instead of function. And it's going to stay false, right? So there is what we just calculated, 0.017 by hand. Now that I've locked these, I can just drag this thing down, and I have just found the probability of 1, 2, 3, and there's our 4, 20.227, just like we calculated before. So there is how you can use Excel to find all these, right? So now I've built my table like I did in 5.1. It's my table because when I drag it down, it messed up my nice table here. Okay. Let's do this for now. Now, if I want to do my CDF from 5.1, remember my CDF is just taking our first event and keeping it the same. And then every other event, I take my previous event and I add the next event. And now, why did that work? No. And I add my next event. I forgot the plus, that's what happened. And if I do this correctly, this should all sum to 1, and it does. So there's my CDF, because my CDF adds up every previous one. We can prove binomial that the formula from 5.1 always works, right? So we've already did n times p on the previous page, which is just 10 times 1/3, which gives me 3.3 repeating, which is what that is. If I want to use the rules from 5.1 again, it's just my x, my event, times the probability of success, right? And then I drag that down. I don't want to drag it down, it keeps giving me extra bars and make my Excel look bad. That's right. Fix it. And then according to the rules, we add them together by using the sum function. You can see we get the exact same answer. And variance, I can take I'm trying to remember the variance formula off the top of my head. I'm going to cheat and go back to this one. There we go. It is my event minus my mean squared times the probability. I don't like the shortcut formula because I can use Excel to do this real quick for me. So my event minus the mean quantity squared times its probability. And then I'm going to lock my mean because I don't want that to change by hitting function F4. And then I drag it down. And that's why I got this video, so you can play around with it if you really want to use Excel. I know I'm going a little fast, but you can pause it and go through it. Again, I want current no borders, and then put in my nice border. And so that's how I created this whole table. And remember, the good always way to check your probability distribution function, it should sum to 1, and mine does. So that's how you can use Excel to find binomial. And of course, you don't have to build the table, right? If I want you to find the probability that x equals 4 again, so that is this equals binomial dist. My x is 4. My trials was 10. My probability of success was 1/3, and I am looking for it to be equal, so that's my mass function, and I can still get it. But once I build my table, I have all the answers, and I can just build it real quickly by doing the click and drag. So there's how you use Excel to do the binomial distribution. All right, the next thing we're going to talk about is the Poisson. I will come back here to Excel in a minute once we know what Poisson is, and show you how to use Excel to do Poisson. So let's go back to our OneNote. Go to Poisson. So what is a Poisson distribution? So a Poisson distribution basically returns the probability of an integer number of events that occur within a given, I put time period because most of them are timed, the book says interval. So you could have other intervals, but you must have it within a specified interval. Typically that interval is time. You must know the expected number of arrivals in that interval or time period, which is mu. So the good news when you do Poisson, you will know what your mean is already before you even start calculating anything. And the Poisson is also interesting that the mean and the variance are exactly the same. So once you know your mean, you also know your variance. So the Poisson distribution formula is E, which is exponential. That's that little E on your calculator. It's like 2.7182, I can't remember any numbers after that, but it's on your calculator, so make sure you know where to find E. It's raised to the negative mean, the negative mu. Then it's multiplied by whatever your mean is, raised to the x, which is your event, all over x factorial, which is another counting technique that we learned in chapter 4. So you see a lot of things in chapter 4 are still applied here in chapter 5. So a couple examples of what a Poisson process is. There are a series of independent events, arrivals at stores, banks, anything that occurs in a sequence, basically means they cannot occur simultaneously. Data packets arrive into a router, emails, applications, checkout lines, radiation decay, all these things are examples of real world things that follow a Poisson process. All right, each arrival occurs according to the same process, and the arrivals are independent of each other, which means when one thing comes in, it doesn't increase the likelihood of another thing coming in. And if you don't know your mean, you might have to calculate it by this formula alpha t, where alpha is this arrival rate and t is time. And alpha, a lot of students say it looks like a little fish with tails. It's the Greek letter for A. But you have some kind of arrival rate over some time period. So in class, I kind of talk about this example of new customers arriving at a checkout line in the bookstore every 90 seconds, right? And so what I like to have students tell me is, how could customers arrive? So we could have a customer, every minute. This is over 5 minutes. So 1 minute, 2 minute, 3 minute, 4 minute, and then 5 minutes. We could have 2 customers arrive at the exact same time, and then not have anyone for a while, then a customer arrives, right? And then not have any. We could have no customers arrive at all in 5 minutes. We could have all of them arrive at almost the exact same time, right? Because they can't all arrive exactly at the same time unless they're walking shoulder to shoulder. So they might follow each other in a line, so they all kind of come in at the exact same time. So there's infinite ways to do this. We can keep coming up with different scenarios, right? And that is why with a Poisson process, I guess, remember to use my draw, not with the zoom. With a Poisson process, x goes from 0, because no customers, up to infinite. Now, as my x increases, there will be basically probability gets really, really small, so it's almost nothing, right? Because the probability that I get 10 million customers in 5 minutes is pretty much the probability of 0. So even though it does go on forever, it will go to a point where then my events basically are, the probability of them happen or not, are 0. So an example of a Poisson process, we'll stick with the bookstore case, right, is how many customers do you expect in 5 minutes if new customers arrive at the bookstore at a rate of 1 customer every 90 seconds, right? So we have to remember we have to keep our labels the same. So there are 300 seconds in 5 minutes. So what is the probability that 4 people arrive in the next 5 minutes? So to find our mean, again, our mean equals alpha t, which alpha is our rate and t is our time, right? So alpha is 1 customer every 90 seconds, so that's division, so it's 1 over 90, times 5 minutes, or 300 seconds, so 10 over 3, or I expect a customer, in the next 5 minutes, I expect 3.3 customers. So basically almost the exact same thing we just got for the binomial a minute ago, right? So there was a relationship there too. We'll talk about that in other sections. So what is the probability that 4 people arrive in the next 5 minutes? So again, this is the probability that, I'm gonna put in my draw now. I'm actually gonna use the right draw this time. This is the probability that x equals 4, right? And now I'm just substituting things in, right? Because we know the mean is 10 over 3. So now E is that symbol. It's in your calculator. It's kind of like pi. So it's E to the negative 10 over 3 times, oh, forgot to put what mu is in there. I'll have to fix that. Do it after the video. But that mu should be, not mu, but I'm trying to get a color here. That should be 10 thirds. raised to the 4th power divided by 4 factorial, right? So now if I go to my calculator, again, what I would do is I'd either put the numerator in parentheses divided by the denominator, or if your calculator can just put in fraction form. So I'm going to put mine in fraction form. Find my little E key. So again, I'm on my Casio. So where is my E? Oh, my E is in the top right, right under, above ln. So I hit Shift ln to get my E. Don't put a subtraction. Remember to put your negative symbol, 10 divided by 3. And then I'm going to times that by, I'm going to put in parentheses, just make sure it doesn't mess this up, 10 divided by 3. Raised to the 4th power, all over 4 in factorial for me is, again, right next, basically right next to my E on my Casio. For the Texas, it's on your probability key, same as your combinations. And then I just hit enter, and I get 0.1835. So good. I like to put this example here so you can see it, so that way you can make sure you're using your calculator correctly to calculate a Poisson. So what is the probability at most 2 people arrive in the next 5 minutes? Well, at most means I can have 0 customers, 1 customer, or 2 customers, right? So to do these calculations by hand, I would have to do this 3 separate times. I'd have to do x equals 0, then do x equals 1, and then x equals 2. Or we can use technology. So I'm going to go back to my lovely Excel here. And I'm not going to create the whole PDF in this case, right? So we'll do both again. So the probability that we got 4 customers, right? And then we'll do the probability, parentheses, at most 2. So the probability of 4 customers, remember, x was equal to 4. My mean was equal to 10 thirds. Now, and Excel wants this thing, so knows what it's talking about, so I turn it into a date. I don't want it to do a date, so I'm going to put it as a number. Then I'm going to type it again as 10 thirds. There we go. So there's my mean, and there's my x. So to find exactly, I do equals Poisson dist for distribution. My x is 4. My mean is 10 over 3. And again, I want exactly. So that is a probability of mass function. So I'm going to put in 0 for false, or click on false. And there I get the same exact answer as we did by hand of 0.1835. If I want to find at most 2, I can do it 3 different times. Or remember, at most means CDF. So I can just do equals Poisson dist. My x is 2. My mean is 10 thirds still. And now because I want the CDF, I can put either 1 or click on the true. And there is my at most 2 of 0.3527 or 0.353. And if you want to do it 3 separate times, and add them together, you'll also, or should, get the exact same answer. So here's a quick little video on the aspects of the binomial and Poisson distributions, as well as how to calculate probabilities of those by hand using your calculator. Not really by hand, you're still using a calculator, or by using Excel. There's other softwares out there. StatCrunch will do this for you, Ministab, there's all kinds of things. Your TI-84 can do it. So the book talks about how to use technology to solve different things. But I use Excel most of the time, so I want to show you how to use Excel in the video. All right. Email me or comment on the video if you have any questions. Thank you. Have a good day.